In this related rate problem, we want to look at a canonical tank. And of course the vertex is going to be pointing down because we're going to fill it with water. We don't want the water to just fall across the top. So this particular cone is 10 feet across and 12 feet deep. And we're filling it at a rate of 10 cubic feet per minute. What we want to do is find the rate of change of the depth of the water when the water is 8 feet deep. So I've went ahead and drawn this over here to the side. So let's go ahead and write down what we're given for this particular problem. So we know that in this case the change in the volume, the dV dt with respect to the change in the volume with respect to time, is 10 cubic feet per minute. Okay. Now it may be misleading to think that in this case the radius is 5, although that's true for the big conic or the big cone. That's not true for how much it is when it is 8 feet deep. That would only be true when it's 12 feet deep or completely full. So that means that the height is not 12, but rather 8. So we want to look at how fast is the depth of the water, how fast is the height of the water changing when the height's 8 feet. So what are we trying to find? Well, we're trying to find the change in the depth, which is the height, so that's the change in the height with respect to time. Now to relate all these things together, we're going to use the volume of a cone. So remember, the volume of a cone is 1/3 pi r squared times h. Well, that's a little problematic because we have an h and an r. So we need to figure out a way that relates r and h together. So if I look here, I have a little triangle embedded in this bigger triangle, where this is my given r and this is my h. So I can use similar triangles to make this relationship. Alright, so we know for the big triangle we have 5 over 12, because for the big triangle our radius is 5, and that's going to be equal to r over h. So if we want to ultimately write the volume with respect to only the height, then that means I want to rewrite this and solve this for r. So if I multiply both sides by h, I get that the radius is always 5/12 of the height. So what that allows me to do is make a substitution into my volume formula. So now my volume formula can be written as 1/3 pi, and then my new formula for my radius, 5/12 h, all quantity squared times h. So if I simplify that, I get 1/3 pi times 25 over 144 times h cubed. And although I could simplify that, I'm going to leave it like that because ultimately what I'm going to do is take the derivative. And when I take the derivative with respect to h, or the derivative of h with respect to time, then that 3 will come down and cancel out that 1/3. So let's look at that. If we do dV dt, the rate at which the volume is changing with respect to time, then that 3 times 1/3 will cancel, so I get pi times 25 over 144 times h squared times dH dt, that implicit differentiation there. So it looks like we've got pretty much everything we need. We've got a height. We know that we want to figure out when it is 8, and we've got that this thing is constantly filling at a rate of 10 cubic feet per minute. So what we're trying to solve for is dH dt. So let's do a little substitution. So we've got 10 equals pi times 25 over 144 times 8 squared times dH dt. And so from there, we're going to divide both sides by whatever that decimal approximation is. it allows us to cancel all that jazz over there. So we have dH over dt is going to be equal to 0.28, we'll say 65. And height is just a linear quantity, so that's just going to be feet per minute. So we figure out that the height of this, or the depth, is increasing at 0.2865 feet per minute. So the important part of this problem was realizing that we have to use similar triangles to rewrite the radius in terms of height in order to substitute back into the volume to get this volume equation only in terms of the height. Okay?